So let's just move on. Next speaker this morning will be Takeshi Miyazaki from University of Electro-Communications in Japan, and he's going to talk to us about equilibrium state of quasi-geostrophic point vortices.
Thank you, and thank you for inviting me here. And I will talk about the statistics of quasi-geostrophic point vortices. And showing some background, introducing the quasi-geostrophic approximation. And I show the numerical results for the point vortices of very large number. And after that, comparison with the maximum entropy theory is tried. And we further introduced the simplified patch model and investigate the influence of the vertical vorticity distribution and energy to the equilibrium state. Or you know something like that. So briefly, geophysical flows and the strong influence of stable stratification, Coriolis force. So the vertical motion is suppressed, and motion occurs in horizontal plane. And there appears a coherent structure of vortices in the geophysical flow. And the lowest order approximation of the geophysical flow is purely two-dimensional vortex, two-dimensional flows. And there are many works on purely two-dimensional fluid motion. And as for the statistics of two-dimensional point vortices, also there are many works. Starting from maybe on Sager, he showed the existence of the negative temperature states and the statistical theories, canonical ensemble, microcanonical ensemble, and so on. And very recently, Yatsuyanagi and others performed very large numerical simulation using a special purpose computer, MD Grave. It's for the computation of molecular dynamics simulation, and it can be used to the vortex system too. Then actual geophysical flows now, of course, 3D, and the next order approximation is, I think, the QZ approximation. And fluid motions now have horizontal planes, but at different height, different horizontal motions, and they interact. And the quasi-geostrophic approximation takes account of this interaction. And even in QZ, we can find the coherent vortex structures interacting each other and dominating the turbulence dynamics. And in these years, our group and Deutsche's group made a series of vortex models describing such interactions. And point vortex model has n degrees of freedom, and spheroidal vortex model 2n degrees of freedom, and ellipsoidal vortex 3n degrees freedom. And here we concentrate on the simplest model, point vortex models, and investigate the statistics. And it's a QZ approximation for the continuously stratified fluid and on F plane. And if you change the vertical coordinate appropriately, potential vorticity can be written as a 3D Laplacian of the stream function. And here, for point vortices, we consider the delta function-like concentration of potential vorticity to n points. So each vortex are advected by the flow field induced by other vortices. And we can write down the Hamiltonian of this system, and just like the 2D vortices. In 2D vortices, the interaction energy is a logarithm, but for QZ, the R inverse interaction energy. And summing up the interaction energy for all pairs of vortices, we have the Hamiltonian. And then the canonical equation for motion. And because the vortices moves on the horizontal plane, z axis is invariant, but x and y moves according to these canonical equations. So we have canonical equations, and we are in a good position to do statistical work. And this system has several invariants. Center of vorticity is conserved, and we shift the coordinate origin to the vorticity center. And another invariant is angular momentum, defined here. And using this angular momentum invariant, we can rescale the length scale. So using I and total strength of vortices, we can make the length scale, and maybe angular momentum and length scale, and take it unity. And as for dynamical systems, there are 3 invariants, Poisson commutable invariants. So even 4 vortices can be chaotic. The actual numerical computations are performed on the graph here. It's like a board inside a PC, and its performance is great. It was originally developed for the gravitational n-body simulations and molecular dynamics. And it's some kind of Pullman supercomputer, and we can do the very large simulation of using these boards. I just show the performance of the MD graph and compare the Castle and point vortices simulation. Here, this is an inclined toroidal vortex which is unstable. Okay, point vortices simulation can cope with the castle. But we must be careful for the number of point vortices and the resolutions of the castles, of course. In this case, there are 2 unstable balls, almost same growth rate. So what happens at nonlinear stage is very, very sensitive to the initial disturbance if you introduce willingly or unwillingly numerically. So, as an example is here, it's an interaction of 2 spherical vortices. Marginally stable case, so just exchanging the small part of the vorticity. Again, point vortice. And in this case is larger. In any case, every graph is very powerful. Okay. Oops. And for statistical investigation, we must prepare the initial condition properly. At first, we introduced the random distribution, a uniformly random distribution inside the cubic box, and the green line here. And we suppose the critical energy is here, and maybe it is a zero inverse temperature state, but it was not so. The same vertical distribution, for the same vertical distribution, and radially we use the Gaussian random number, then the ensembles are shifted to a higher energies. And real zero inverse state is here. And first, we show the comparison between the positive temperature state and the zero inverse temperature state. The energy is given here. And in the actual computation, mainly we use 2,000 vortices and sometimes 8,000. Okay, on the left sphere, if you have good eyes, you can see the difference between the zero inverse temperature, higher energy case, and at positive temperature, lower energy case. And maybe it's difficult to see. So we plot the probability density as a function of radius and the vertical height. So in a zero temperature case, the distribution function is independent of the vertical axis. It's uniform in the vertical and Gaussian in the radial direction. And in contrast, in the positive temperature state, we see the some flat region near the center of the vortices. It's somewhat similar to the two-dimensional distribution. But in the lid region, upper and lower lid region, the concentration is more tighter near the axis. And we can see the clear difference between the central region and end region. So we call this end effect. And we performed other computations varying the vertical height of box A, B, C here, and also changing the energies of the system in the positive temperature region and also in the negative temperature region, D, E, F. Before showing the numerical results, we consider the maximum entropy theory, theoretical predictions. And we search for the maximum Shannon entropy state under the constraints of vertical distribution. Because the vertical distribution cannot change because the vortices move on horizontal plane, so vertical distribution cannot change. And also the global invariant angular momentum cannot change, and the energy is conserved. So we introduce the usual Lagrange multipliers of maximum entropy optimization. Alpha corresponds to the P, and beta to angular momentum, and gamma the energy. Gamma is usually called the inverse temperature in the statistical mechanics. And as you can see, it's a very complicated equation, so it cannot be solved analytically, only one exception. If the gamma is zero inverse temperature, these difficult terms disappear and gives us simple answer for the PDF. It's just the Gaussian in the radial direction and independent, now independent of the vertical height. And the constant beta is calculated to be unity using the angular momentum invariant. As for positive temperature state, we must do some numerical iteration to have the converged VDF. And somehow we can do it. And green lines are theoretical maximum entropy predictions. And generally, good agreement with the red line, numerical, and red plots, numerical plots. But it's very difficult to find out converged solution because the functions of R and G. So it's very difficult, and iterations computationally too intensive. So it's difficult to do the parameter scanning using such complex PDF. So we further simplified the problem, and radial distribution approximated by a top hat-like distribution. So only the patch radius, it can be the function of vertical Z. And in this case, the in this case, the computation is rather simpler, so we can do the parameter scanning using this patch model. So, show you the results for the changing the vertical height for the positive temperature state. If the height, box height is made higher, the two-dimensional region enlarges, and sharper end effect can be found. Yeah. So also this shows the distribution of the angular momentum as a function of the z normalized vertical coordinate. And also the red line shows the sharper end effect. Okay. And next, we consider the influence of energy. And case D is the lowest energy case computed. And we find the sharper end effect again here. And case F is the highest energy considered in our simulation. The distribution is completely different from the positive region. We can see the concentration at the center plane, vertical center plane, is very tightly gathered to the axis of symmetry, and top and lead region, wider distribution can be found. And it shows the angular momentum distribution, and we decrease the energy. Yeah, here is the zero temperature, zero inverse temperature state flat. And if energy is lowered, the center region expands and lead region shrinks. And inversely, if energy is increased, the center region shrinks and lead region expands. The similar things can be found by the patch model, simplified maximum entropy theory, the same trend. But the energy level is somewhat different because patch model can produce the rather low energy state. So comparison is only the qualitative one. And for the physical interpretation of this phenomenon, it can be considered in this figure. And for the vortex cloud, if the vortex cloud expands, the entropy increases. And also the angular momentum increases, but energy decreases. And as for the entropy and angular momentum, each horizontal layer has the same contribution. But as for energy, the center region has a dominant contribution. So for higher energy, center region must shrink. Then to keep the angular momentum unchanged, lead region must expand. This is why such distribution can be found. And also for positive temperature state, lower energy, center region expands and lead region shrinks. Okay. This is the physical interpretation of the distribution. And as for the vertical distribution, we can introduce the other possibility. For example, it is a parabolic vertical distribution. It's like a spherical vortex patch. And in this case, here, as you can find, it's a rather lower energy case, the very sharp end effect of the whole top and bottom. And again, the patch model can work relatively well. And as energy changes, the angular momentum again expands in the center region and shrinks at the lower and upper and lower region. And it plots the patch radius, changes of patch radius. As energy is lower to the lowest level, the lowest level is the uniform potential vorticity vortex patch solution. And so it shows that a spheroidal vortex patch of uniform potential vorticity seems to be the maximum entropy state in the limit of lowest energy. So patch model computation do the lowest energy vortices. And my summary here. Using the MD graph 3, we have the axisymmetric equilibrium state. And at zero inverse temperature, Gaussian in the radial direction distribution can be found, and uniform in vertical direction. And for positive temperatures, end effect near the upper and lower is found. And if end effect can be more sharper if the box height becomes larger. And for negative temperature, inverted end effect are found. And generally, maximum entropy theory give good agreement for the direct simulation. And we consider the physical interpretation of the end effect. And finally, for parabolic vertical distribution, we find that in the limit of lowest energy, a spheroidal vortex patch of uniform potential vorticity is the maximum entropy state. Thank you.
Have you thought about generalizing this idea to not just one sign of vorticity, but to two signs,
Yes,
not mixed horizontally, but in the vertical? So
you mean the phaeton-like thing?
Yes.
Yeah. Yes. Now we are doing the such simulations.
That'd be very interesting because there are instabilities that you don't have.
Yeah. And also, you can consider the various cases. And for example, plus and small plus or something like. And in the limit of small plus, the scalar can be considered. So we can compute the scalar distribution using M-degree. Okay.
Very nice.
Questions?